Let us consider some examples. Let us calculate such an integral by ab of x squared plus y squared plus z squared dl, where L is interval of straight line AB. A is 1, 1, 1, B is 0.303. First hand we have to write down parametrical equation of this straight line AB. X minus 1 over 2 will be y minus 1 over minus 1 will be z minus 1 over 2 equals t. X minus first coordinate divided by 3 minus first coordinate, and so on with everything. And each of these parts equals t. From here we express t, we'll get that x equals 2t plus 1, y is minus t plus 1, and z is 2t plus 1. And we have point A correspond to t equals 0 and point B correspond to t equal 1. Let us now find differential of this curve. dl will be square root of x prime by t square plus y prime by t square plus z prime by t square dt, which will be square root of 2t plus 1. Derivative will be 2, so we'll get 4, plus derivative of minus t plus 1 will be minus 1, square of it is 1, and same for z will be 4 dt, and we will get 4 plus 1 plus 4 is 9, square root of this is 3 dt. Now we try to calculate our integral. We substitute everything here. X is 2t plus 1, y is 1 minus t, and z is 2t plus 1 dt, and we get 3 dt actually here. And integral is going from 0 to 1 because 0 and 1 are corresponding values for points A and B. Now we open the brackets here, we get 9t squared plus 6t plus 3 dt, and if we calculate everything we get 9t cubed plus 6t squared by 3 over 2, which will be 90 squared, plus 3t by 3. And this goes from 0 to 1, and in the end we get 27. Second example, we have integral by L y dl, where curve L is specified by equation y equals x cubed. X is from 0 to 1. Here dl will be calculated as 1 plus y prime by x squared dx, and will be 1 plus 9x power 4 dx, square root of it. And we are going to substitute everything with x, so our integral by L y dl will be integral from 0 to 1 because x changes in this interval. We'll get x cubed because y is x cubed, square root of 1 plus 9x power 4 dx. Now we can bring this x cubed inside our differential and make actually 1 plus 9x power 4 inside dx. To do this we have to move out 1 over 36, integral from 0 to 1, square root 1 plus 9x power 4 d of 1 plus 9x power 4. Now 1 plus 9x power 4 is a variable, not a function, and we just have to integrate power 1 over 2, which will give us 1 over 36 by 2 over 3 by 1 plus 9x power 4 in power 3 over 2 from 0 to 1, and substituting limits, we will get 1 over 54, 10 square roots of 10 minus 1. Next example, if we have integral by L, square root of x squared plus y squared dl, where L is specified as polar curve. A 1 plus cosinus phi. Phi is from 0 to pi. Actually, this is a cardioid curve, which looks something like that. For this interval, if we have phi from 0 to 2 pi, we'll get same element here. Now, to calculate dl, we calculate rho prime square plus rho square d phi, and here we'll get derivative of this function will be minus a sinus phi, because a by 1 derivative will be 0. So we get square root of a square sinus square phi plus a square 1 plus cosinus phi square d phi, and in the end transforming it, we will get a, we can move out a out of the roots, sinus square phi plus 1 plus 2 cosinus phi plus cosinus square phi d phi. Now, sinus square plus cosinus square is 1, and 1 plus 1 is 2, so we'll get a square root of 2 plus 2 cosinus phi d phi. Now, we have to somehow deal with this root. To do this, we have to move out 4 out of this root. We'll get 2a square root of 1 plus cosinus phi over 2 d phi, and this expression is the same as cosinus square phi over 2, so we'll be getting 2a cosinus phi over 2 d phi. Now, returning to our integral by L square root of x squared plus y squared dl, we will get integral from 0 to pi a by 1 plus cosinus phi by 2a cosinus phi over 2 d phi. This part is actually rho, because square root of x squared plus y squared is rho. If we make this substitution, if we make this change of coordinates. Now, integrating this function, we will get 8a squared, integral from 0 to pi, cosinus power 3 phi over 2 d phi over 2. And now we can use Wallis formula. We'll get 8a squared multiplied by 2 over 1 by 3, which will be 16 over 3a squared. Let us now find length of a curve rho equals 3e power 3 phi over 4, where phi is from minus pi over 2 to pi over 2. Formula for length of curve is integral by L dl. So now we have to find dl. We have polar curve, so we get derivative of 3e 3 phi over 4 will be 9 over 4e in same power, and to make it square, we get 81 over 16 e power 3 phi over 2 plus square of the function itself, 9e 3 phi over 2 d phi, which will be 15 over 4 e power 3 phi over 4 d phi. And now substituting this dl in our integral, we get that length of curve will be 15 over 4 integrals from minus pi over 2 to pi over 2, e power 3 phi over 4 d phi, which will give us 15 over 4 multiplied by 4 over 3 by exponent 3 phi over 4 from minus pi over 2 to pi over 2. And we will get 5 exponents 3 pi over 8 minus exponent minus 3 pi over 8. If we simplify this a little bit, we'll get 10 by exponent 3 pi over 8 minus exponent minus 3 pi over 8, which is 10 sinus harmonic of 3 pi over 8. One more example. When we try to find mass of curve with density 2z minus square root x squared plus y squared, which is specified by equation x equals t cosinus t, y equals t sinus t, and z equals t. T is from 0 to 2 pi. We find mass of curve using formula integral by L of mu dl. Here dl will be square root of derivative of x will be cosinus t minus t sinus t square plus square of derivative of y will be sinus t plus t cosinus t square, and plus derivative of z will be 1. If we open these brackets, we get cosinus square t plus t square sinus square t minus 2t sinus t cosinus t plus sinus square t plus t square cosinus square t plus 2t sinus t cosinus t plus 1. We get these two elements destroyed, and we have cosinus square plus sinus square, t square sinus square plus t square cosinus square. Sinus square plus cosinus square is 1, so we will get square root of 2 plus t square dt. This curve is actually a conical line which will do something like this. So it will be. So this curve will be coiled around a cone. Now let's calculate its mass. Mass of a curve will be integral from 0 to 2 pi 2t minus square root t square cosinus square t plus t square sinus square t, and everything is multiplied by square root of 2t plus t square dt, which is equal to integral 0 to 2 pi t square root of 2 plus t square dt. And we can move this t under the differential. We'll get 1 over 2 integral from 0 to 2 pi square root of 2 plus t square d 2 plus t square, and in the end get 1 over 3 2 plus 4 pi square power 3 over 2 minus 2 square root of 2, which will be mass of our curve.